Types of radioactive decay can be broken up into two main categories: those that change the mass number and those that do not. The purpose of radioactive decay is to bring an unstable nucleus into the zone of stability. If we have a look at this graph over here, there is a zone of stability along these elements that follows this approximate line of a 1-to-1 neutron to proton ratio. This is followed very closely with the lighter isotopes and elements, but as the nuclei get heavier and heavier and more protons are present, more neutrons are needed to make that a stable atom. So around here, that ratio might be 1.3, and up here it might be 1.5. That's the idea. Any element or isotope that's outside of the zone of stability is going to undergo nuclear decay in order to get it to a nucleus that is stable. So with that in mind, let's look at the different types of nuclear decay. We'll begin with the types that don't change the mass number. The first one is beta particle production. A beta particle is an electron, and here it's visible that the mass number remains the same. What does change is the proton count. Here 89 protons are present, and then once it undergoes this beta decay, the proton count increases by 1 and gives off an electron or a beta particle. So this might be a type of decay that happens in this region up here somewhere. In this part of the graph, the ratio of neutrons to protons is too many. So in this type of decay, one of the neutrons turns into a proton. Because the mass number remains the same, there are still the same number of protons and neutrons, but there is an additional proton, which means that a neutron changed into a proton. Next, positron production. Positron production is similar to beta particle production. Instead of an electron, though, it's a positron, which is an electron but with a positive charge. Now, normally people don't come into contact with positrons that often, because when an electron and positron combine, they annihilate each other completely and become energy, and I think neutrinos as well, but maybe not. Maybe that's something else. But regardless, they basically completely annihilate each other, and it so happens that there are more electrons in the universe than there are positrons, so that we don't see them very often. If they're produced, they're almost completely annihilated the second they are produced. But this is a product of this type of decay. Still, the mass number remains the same. But in this situation, a proton is changed into a neutron. 13 protons and neutrons, 7 protons, and now there are 6 protons. One of the protons is changed into a neutron and produced a positron. So this might be something where there are too many protons. Something down here, by eliminating one of these protons, now it's further up and it's closer to the zone of stability. Electron capture. This is basically the reverse of beta particle production. Here, a nucleus takes in an electron. It actually captures one of its own electrons. People have asked before if it is possible for an electron to fall into a nucleus, and the answer is yes. This is what it is, electron capture. Here we have a nucleus and an electron. The mass number remains the same. But the proton count is reduced by 1. By taking in this electron, there is a process that occurs, and there is one less proton. And this is actually an interesting one, because here mercury is turned into gold. So that probably would have interested alchemists back a long time ago. They're looking for the wrong element. They should have been looking for mercury, not lead. But if you have a look at this, it's basically this backwards. Here it's giving off a beta particle. Here it's taking in a beta particle. Here the count is being increased by 1. Here the proton count is being decreased by 1. So this about sums it up for the more common types of radioactive decay where the mass number remains the same. So now we'll have a look at situations where the mass number changes. And the first one is alpha particle production. And an alpha particle is a helium atom. The mass number has changed. Basically, it just subtracts whatever a helium atom's count is from the total. So here it's 210 and 84, the proton count. A helium has 2 protons and 2 neutrons. So 4 is going to be subtracted from this number, and 2 is going to be subtracted from here. And it's left, we go from polonium to lead. 206, so subtracted 4, 82, subtracted 2. Next is spontaneous fission. Spontaneous fission occurs when a large nucleus breaks up into 2 smaller nuclei of roughly around the same, roughly about half each, but it can be closer or farther, but it's not like it releases a smaller particle. These are, it's very close to being cut in half. So here, 2 nuclei are produced that are they're roughly about half each, and neutrons are released. So this is something that would occur in a nuclear reactor or like an old atom bomb. I think most of them are like hydrogen bombs now, but still they're going to use something like this where it's going to create radiation. In a hydrogen bomb, it doesn't really create that much radiation. So this is going to split into 2 atoms. So this is basically what is occurring for something like this. They're taking uranium-235 and bombarding it with neutrons. Turns into uranium-236. And then this occurs. So this occurs in a nuclear reactor. That's why they have those control rods. Because this is going to go and hit a bunch of more uranium-235, and then it's going to cause a chain reaction, basically. These 3 neutrons will do this to 3 more uranium-235s, and then 3 more, and then 3 more, and 3 more. So that's the idea of it. That's spontaneous fission. This is what happens in a fission power plant. And the last one is a type of radiation that, well, this basically is, well, let's just talk about it first. It's gamma ray production. And it happens when there's an excited nuclear state, and in order to get back to a ground state, it releases energy. It's very similar to the way an electron can become excited and reach a higher energy level. And in order to get down from that energy level, it releases a proton or a photon. It's the same thing with the nucleus. It's in an excited state, and then it releases high energy photons or gamma rays and goes back down to the ground state. Now this occurs basically alongside of all of these other reactions. There's always going to be gamma rays released. But this one is off on its own. I put this one off on its own because it doesn't necessarily, this can happen on its own. Some nuclei can get to an excited nuclear state but not undergo any of these other types of nuclear decay, just emit gamma rays. While these other ones, it's they change, and they change protons, neutrons to protons, or they change in mass number. this does not necessarily have to change the mass number or change a proton to a neutron or vice versa.